This stream is just gonna be me reading a paper. I came across this paper today from a blog post, and this is, I guess, released in this year, so reasonably recent. And I'm interested in it because it seems to be relevant to my area, which is sampling, but this is apparently for discrete distribution. So this is a short paper too, so which is always nice. And at a reasonably good conference, ICML, this one, or what do they call it now? PMLR? Okay, I don't know, it's the ICML conference. So let's just go through this real quick. Hopefully it wouldn't take too long. I don't expect this to take longer than, I don't know, 15-20 minutes maybe, depending on how specific I want to understand the thing, how deeply I want to do it. Okay, let's just go right ahead. Okay. Oh, hi. Wait, this is strange. So someone's following even though they're not viewing the stream right now? Or is my view counter not working? Okay, either way. Could be a bot. Don't know, right? Okay, so we seem to be looking at a method that's able to sample from discrete distributions. So distributions with discrete variables, so not continuous. And somehow is able to take gradients. With respect to it, I don't know much about discrete things at all, so this is all new. With respect to discrete inputs, the proposed updates in the Metropolis Hastings sampler, we showed that this works well in a bunch of examples, and it does better in training deep energy based model on high dimensional discrete data. Okay. Give bounds that the approach is near optimal in the class of samplers which propose local updates. Okay, sounds clean, sounds like a very clean idea. Let's go. Right, okay, so this is saying that most continuous stuff works because we are able to do some type of differentiation depending on, of course, the method itself. Sometimes you don't need to, but oftentimes it's quite helpful to be able to take some type of local information of the function. Block independence, I don't know what that is. I mean, okay, I guess. Oh, never heard of block independence. I mean, I've heard of it, but don't really know too much. Okay. Yeah, this is one of those things that maybe it's just me, but I also found it, I mean, I've always found it a bit confusing that you can have a picture here, and then the part of the article that references that picture is maybe, I don't know, somewhere in the next page. Then you have to scroll back up to look at the picture, and if you look at it now, sometimes it may be confusing because you don't, there's no clear explanation of it. So I'm always don't know what to do when I see this. It looks nice, I mean, it looks like a good picture, so okay, let's look at it. Often discrete distributions are defined by a continuous functions whose input is restricted to a discrete set. Oh, okay. Restrict R2 to Z2. We use Taylor series computed on the underlying continuous function to estimate likelihood ratios. Oh, to make discrete moves. These estimated likelihood ratios are used to inform proposal distribution over moves in the original discrete space. I see. So it's saying that. Wait. So a continuous method would simply be to take the okay. So it is taking the approach of using actually an underlying continuous operation, and then you just restrict it. Okay. We'll see what that really means. I still don't understand it very well. Gradients of this one. adaptive Gibbs sampler or a fast approximation to locally informed proposals. Okay. Okay. I've never really used the POTS model, but maybe I'll get to play with it sometime. Okay. Okay. So this is like the okay. So this is a, and this is I guess a prior. Oh no. Oh, this is the. Oh, okay. Sorry. This is the target. This is the. Yeah, the lock. And this is the constant. D-dimensional binary and categorical, as well as finite dimensional discrete. That's all. Okay. Okay, one hot coded. All right. So one hot coding just means to kind of reduce everything to binary information. Yeah, so if you have A, B, C, A would be 0, 0, 1, B would be 0, 1, 0, and C would be 1, 0, 0. It's just a kind of a naive way of doing things, but you know, it works very well. Okay. So the problem with Gibbs sampling works really well. It's rejection free. The problem with it is that you need to know the conditionals. Yeah, if you have if you have a independent structures, then you don't have the conditional. It's just the marginal, right? If I don't quite understand this part. So if you do not have independent structures, we can let so we do not have a block, so we just take one dimension. It's simply one-dimensional categorical distribution over k possible outcomes. Over k possible outcomes? Okay. Which requires k evaluations of the unnormalized log density. I assume so, because you are doing this each one for a different one. We typically fix an ordering of the dimensions and iterate through this ordering to ensure that each dimension is updated. Okay, so that means you're doing just a coordinate-wise update. Why do I look so yellow? Wait, maybe let me turn off my lights. It's okay, it's significantly darker actually, but you know, whatever. While simple updating one dimension can be problematic, consider an example of binary model of the MNIST data set. Almost all dimensions will represent the background, and if chosen, wait. What are you updating here? Sorry, I don't understand. What are you updating? What's a binary model? Like, is it something specific, or is it just a generic use of the word? Okay, so I guess this just means that a 1 and 0 a representation of the MNIST data set, and we have to update this model. Yeah, it will not change ideally. Okay. We could build a more efficient Gibbs sampler, that's true. Consider Hastings with proposal, where I is a distribution over, where Qi is a distribution over indices. So you propose the index, you over indices, and Qxi equals to delta x prime equals x. Oh my god, with the construction. X prime equals x minus I. Dirac delta. What does this mean? What does this mean? X prime, is it an assignment or is it an equality? What is it? This is equals to this. Proposal what? So you select an I and then you take the complement. So given I and then you complement. So this is the delta if I don't really know what it means. So what? So they all have to be 1? Wait. What is going on? I'm pretty sure I'm understanding this wrong. With this sampler, we will first sample. This is already taking longer than I expected. Okay, shit, let's move faster. I don't think I need to know details anyway. For example, I, yes, then flip the i's bit of x to obtain x prime. Oh, che, and then accept this proposal with updated. Why is it like this? Oh, because this is log. Okay, because f is log. Okay. And then 1. So you take the I, first sample index I, flip it, to obtain x prime. Still a bit confusing, this part. I don't know the notation. I mean, I'm not. Yeah. I don't understand it super well. So this is saying the complement. So the well. Okay, I don't care. Okay. Yeah, but just follow this. So you take I, flip it, and then you accept it with some probability considerable if Q is biased towards dimensions. Okay. But I need to then compute this thing, I guess. Considerable has been done using prior sampling data to adaptively update I while maintaining the validity. Revisiting, we see a most pixel likely to change are those at the edge. Yes, where the edge is considered depends on the entire output. Where this edge is varies. Where this edge is varies considerably, and thus we can imagine an input dependent proposal should be able to outperform an unconditional, I guess, using gradient to inform proposal. Okay. What the hell is a Hamming ball? Is Hamming ball like ball but discrete? Like Hamming as in Hamming code. What's a Hamming ball? What is a Hamming ball? Hamming distance. Okay, so it's something like a ball, but in a discrete context. Okay. Okay. Hamming ball sampler. Yeah. Okay, maybe I don't understand Hamming stuff so well. Uh-huh. Yes. Flipping each bit with I guess. Where does this come from? Two x minus 1. What? And what is this? What product is this? Oh, I think this is, wait, my intuition is telling me that this is like it's just a trick really, to get the, so if it's as -1, hey wait, sorry, is 1 and 0, 1 and -1? 0 and 1, yeah, so if it's 0, then this would just be 1, and then if this is 1, then this would be -1. So it's something like changing it into -1 and 1, something like that. Okay. So Taylor series to approximate likelihood ratios within the local window of point x. Window. I mean, my guess of what a window means is like one, like the distance. Well, the where you do your approximation and how far away that's the window. So I guess it means neighboring well, I don't know. It possibly means neighboring transitions or neighboring iterations of your adjacent samples, if you will, of your Markov chain. What the hell is this? Oh, okay. Gibbs with gradient. Okay, so let's look at the algorithm. So on normalized current sample, compute D. If binary for is categorical. Yeah, so now if you look at this, now that more think about it, right? If this is 0, then this is 1. Oh wait, 0, then this becomes 1. And then if this is 1. Oh wait, if this is 0, this becomes 1, and this is 1, this becomes -1. I don't know. It feels like that to me. I don't know. If by any chance any of these authors happen to chance upon this strange video, then yeah, let me know. And I'm sorry if I'm completely misunderstanding the point of your work. I am trying. Okay, categorical softmax. Categorical is here, right? It's just, yeah. Oh, then there's the, wait, there's that. Okay. Huh. Alright. So compute your this, then you flip it, then you compute that, and then you just do your usual update. Asymptotic variance, spectral gap. Huh? Isn't this just the definition of the spectral gap? Why is it? Oh, okay. Yes. Oh, okay. Yeah. Whoa, this is cited. This book, is it a book? Or is it a paper? Cited 3,000 times. Damn. Okay, anyway, yeah. It's a book. It's a book. This is the approximation, right? Oh, that's an interesting question. Why hasn't this relatively simple method been proposed before? Okay, so it kind of has the at least the main feeling of the method kind of is has existed, but doesn't work very well. Use discrete distribution to create a related continuous distribution relaxation whose samples can be transformed to samples from the target distribution. Okay, then that means you do it on the continuous regime. This is important. Mixing here does not imply mixing there. We need to mix everywhere. Well, that's not true. You just need to mix in this discrete space, right? What am I talking about? Oh yeah, true. Hey, this is true. There's no hyperparameters. Hey, that's nice. Okay. Okay, and I think that's about the main idea. Okay, so I guess the main idea, which is that you use a Taylor series expansion of your continuous function on which you put a restriction in your inputs such that it is discrete. But never mind, you stay in the continuous place, you stay where you are, continuous regime, and then you do your Taylor series approximation as well as your gradients, you get it there. Then you use it to propose discrete moves, and you can kind of compute all these things, the usual Metropolis-Hastings steps, fairly straightforward actually. And then it showed that it is at least C times more effective than the usual kind of locally locally balanced proposal. Yeah, so where did they say it? Locally informed. Okay, yeah, so they use this locally informed method. Okay, that's cool. Alright, I'm gonna stop the stream now, and I'm gonna move on to what I really want to do today, which is to write my paper. Alright.